All right, let's continue where we last left off. There's just a little messy overview of kind of the idea of the vertex shader and the fragment shader. What we went through last time was kind of these variables, mainly looking at uniform variables, where we take these kind of globally accessible variables in the shader that the main function can use, that are called uniform variables that we can set through our code. And we looked at how we define these variables, how we set them, how we kind of get a handle for them into our own Java code so that we can send values to that handle that will then be set in the shader. We looked a little bit at varying variables as well, but we're going to look much closer at those now. So we're going to see how we can use the varying variables to get more communication between the vertex shader and the fragment shader. So in the vertex shader, we also have these attribute variables, the vertex lists that are sent into OpenGL, because the vertex shader is kind of the starting point of the OpenGL pipeline. Attribute variables aren't present in the fragment shader. However, in the fragment shader, we also have uniform variables that are just fixed values that we can put in anytime we want, and they're just constant throughout the run of the shader. But here we have the varying variables as well as input variables, whereas they're output variables in the vertex shader. So let's look at the program a little bit, what we had last time. What I want to do is just start with exactly what we had last time. Then see if we can simplify it a little bit. Okay, here I started out kind of at a dark side of this cube. Since we have a fixed light position now rather than a light that's kind of following the camera. What I want to do is take all of this kind of clutter and motion out of the scene and start by going into our display function here and just look at the look a little bit at the objects that we're drawing here and kind of simplify this. I think it would be simplest to just take all but one out. We have, you don't normally start putting in shininess here. Let's at least take this out. Here we have pop and pop. Where do we have push for those? So let's just start by drawing one thing. Just make sure we set some values for everything here. So we're setting the eye position, the light position, and the light color. Then we have specular and diffuse. Okay, no need to do that twice. Change the order around a little bit. So we have diffuse, which is our main color. Go back to no specular and some simple reddish color on this, and just draw a solid sphere. We have a pop matrix here that wouldn't do anything unless we had a push matrix. Okay, we have a push matrix here, so after this pop we just still have an identity matrix. We're moving this nowhere, we're scaling it by 2, just to see what this looks like. So this is a sphere in the center, and now I'm moving the camera around it. If we can start the camera in a nicer place, where does the light start? The light position is always 10, 0, 0. So let's just start the camera there as well. The camera starts out at the same place as the light. Okay, so we look at this sphere from exactly where the light is. Then we can move on to this side. All right, so this is the diffuse light only. We can see that our moving around really doesn't have any effect on it. It's hard though. What we should probably do is to add another object behind this one, just so that we have some reference of how we're moving here. Let's simply copy this code, copy the entire thing. So, okay, the first object we're going to draw, let's make it fairly strong blue color here. No specularity, and let's draw it as a cube. So that should be translated a little bit backwards. So where were we in the light? We were at 10, 0, 0. Let's just put this at minus 10, 0, 0. Okay, so we see the sphere there, and now I can see the box behind it. So at least you can see a little bit of where I'm moving. So it gives us a little bit of a reference to what I'm doing with the motion of the camera here. Okay, now let's add in the specular. So what I did last time is I said, let's just make the specular fully white, so we can completely see kind of, or have a better idea of what's the diffuse part and what's the specular part. We could even do it more clearly by having it separate colors. Oops, set it on the cube instead of the sphere. Sphere is a lot nicer to kind of see these subtleties. It's a simulated smooth surface. All right. Okay, so we can see that there's this extra shine spot there in the center, and it kind of moves around. We know that when I'm here, I'm kind of looking at it from the same direction as the light, so it's just reflecting directly back. When I move to here, it moves to this closer to the same side that I'm looking at it from, but not entirely to the same place I'm at. It kind of moves to the spot in the sphere that's in between the direction to the light and the direction to me. That makes sense, because that would be the spot where the light reflects into the eye of the camera. We can see that by moving around, did I not? Okay, I hadn't implemented anything to move myself directly up and down. We can see that this kind of goes on. However, we can see that the detail isn't great in this, and particularly if we go close, start seeing that we're not really getting any very strong shine spot here. You can see that it's a little bit stronger here and here than it is elsewhere, but this is not kind of, none of these places that we see brighter is the actual place where it would reflect directly into the eye. Does that make sense? That would probably be somewhere around here. However, since that spot isn't hitting very close to any vertex, so we have a vertex here, we have a vertex here, here and here, it's hitting in the middle of a polygon, then we get a calculation in the vertices for a color or for a specularity intensity, and then this intensity isn't that high here, here, and here. It would be very high if we could calculate it exactly here, but since that's not in an actual vertex and we're doing these calculations only for the vertices, what we end up with is, you know, when we move further to here, oh, then we can see that this shine spot kind of hits right on the vertex, and then we get that clear shine spot. Move a little bit away from it, and again, we lose this clear reflection spot, this shine spot. Does it make sense to you why this is happening? Do you see how this is happening, or do you want me to draw like a little diagram of it again? Right, that's cool. Okay. But if you like, we can kind of draw this up. The idea, though, is here I'm getting the shine spot directly on a vertex where I do a calculation. So then the question is, how can I change the calculations that I'm doing so I get this shine spot all the time? And also, so I stop getting these kind of stronger lines along the edges of polygons, but just get all the calculations wherever I want them, not just in the vertices here exactly in these points. So if we look at the vertex shader and fragment shader again, the vertex shader happens once for each of these vertices. Then the values that we get, the values that we put into the varying variables, in this case that's just color. So the color is simply saved with the vertex, and that color of the vertex just hangs with the vertex throughout the pipeline. When we get into rasterization, where we start filling in the space between vertices, when we actually fill in the pixels that the polygon will fill, then we simply take this color for each vertex and we do these weighted averages between them to fill in the vertices, no, fill in the pixels, sorry. So if we don't get a bright spot here, and we don't get a bright spot here, and we don't get a bright spot here, and then we fill this triangle in with the pixels, obviously none of the pixels will be brighter than any of the values for the corners, values for the vertices that are being averaged out. So then the question is, how can I, because this is the mechanic that I have, I can save a value for each vertex. In this case, I save the color for each vertex. When I get to the fragment shader, everything that I put into a varying variable will be averaged in this way. And then that value for each pixel will be stored in the same named varying variable in the fragment shader. Or we could call the fragment shader the pixel shader. So the fragment shader is run once per pixel. What we do is we simply take that weighted average and we set that to the color. So the idea here is, if we just store the final result and then average that over, we get this this result. If we want a nicer result, if we actually want to do the lighting calculations in the fragment shader, so actually do the full lighting calculations that we're now doing in the vertex shader, which is basically this: calculate Lambert, calculate Phong, calculate the color, actually do these calculations for each pixel, then what values should we average? Because then we can't just calculate the color here and average that. We need to take some values that we get in the vertex shader and set them to these temporary variables, so to speak, these varying variables, get those averaged for each pixel, and hope that we get a better result. Does anyone remember from last time, kind of, I quickly talked about this, what it is that we would like to average instead, what our varying variables would be instead? Okay, vectors. So let's, all right, the v vector. So the s vector is the direction to the light, the v vector is the direction to the camera, the vector normal here, which here is an attribute value, but then we've multiplied it with a model matrix, so we have the normal in global coordinates. So we have these directions, the normal, which is how the surface is facing, the direction to the camera, and the direction to the light. In the end, the absolute values of these doesn't matter as long as they're all in the same relative space. So relative to each other, the normal, the direction to the light, and the direction to the camera, we have these relativities. We have these kind of ways to calculate these angles. However, if we go ahead and calculate these angles already, then we've kind of taken information out of it. So if we start our calculations and get them to here, or to here, and say, I'm going to start with these calculations here, then I'm going to postpone the rest of the calculations until in the vertex shader, then that hopefully will mean we can do these calculations for each pixel, but still we've calculated what we need for each vertex, because it's cheaper to calculate something for each vertex. We want to do as much as we can in the vertex shader, but only what's necessary to get the results that we're looking for. And since now we've decided that our results aren't good enough, we want better results, but we want to do as little as we can. So we're going to go this far. And then the question is, do we need to take the normal into an average, into a varying variable? Yes or no? Yes, I would say so, because you can have a separate normal on two different vertices in the same polygon. When we're doing a smooth surface like the when we're doing a smooth surface like the sphere looks like this. It's actually represented with polygons, but we have these normals to the surface aren't exactly the same, even if they're part of the same polygon. So we need to average those. We need to say, okay, we get one normal for this vertex, another for this one. When we average it between the pixels, we'd like to get, different normals, ranging, gradienting from this normal all the way over to this one. So yes, the normal would be one of those. That's the direction to the light. Would that be one of the ones we want to say? So if we have a light here, oops. If we have a light here, and this is the direction to the light here, it's a little bit different here, so we'd probably want to get that gradient as well from here to here. So the direction to the light, yes, we would want to put in a varying variable. The direction to the camera, do we need that in a varying variable?
Yeah.
We could put that in a varying variable,
or you could just put
and then calculate h in the pixel shader and the fragment shader. But yes, like you say, we could also calculate h all the way here and just say, let's put h in a varying variable. We can take our calculations one step further in the fragment shader, no, in the vertex shader. Because we can see that in the calculations that we're going to do in the fragment shader, we're using S, and we're using normal, and we're using H. So these need to be sent over. And not only sent over, but kind of averaged over the entire range. I'm going to wait a little bit, or not wait, I'm going to see if I can save these shaders here. To begin with, let's make sure everything works correctly now. Okay. Let's close these. Let's see if I can copy and then paste these. Simple 3D. Pixel lighting. Simple 3D. We're going to say this is per pixel lighting or per fragment lighting. Here, and then let's rename these. And say this is simple 3D vertex lighting. And rename this one as well. So I'm simply saving what we have so we can compare and contrast rather than ruin what we already had there. Okay. Some things will need to change. I'm going to go in here and say continue with the vertex lighting and make sure everything works. It's also just good common practice in complicated systems. Do a little change, even if I didn't do any change now, just refactor it a little. Make sure everything works before you start changing more. Otherwise, we might have an error. Think that that error is because of some of the changes we made, when it's actually because of, a copy-paste error in my refactoring. All right, so let's look at this problem again. I go close, I go here in between, and I can find these spots where I don't get the shine spot anywhere. It's somewhere between vertices. Okay, I did something I wasn't going to do. I hit code blocks. All right. So, questions this so far? So what I now want to do is I want to take the pixel lighting one. I want to open those. So the vertex shader, and here's the fragment shader. Okay, now they're the same, but now we're gonna do some changes. So now my question is, just off the top of your heads, if you're thinking about this system, last time we were adding uniform variables. We were adding the way we need to talk to the shader. We were changing the way our program actually talks to the variables. We were adding variables, so we need more communication between them. If we're going to make the change we were talking about now, do we need to change the system outwardly? If we view the entire shader program with fragment shader and vertex shader together as one black box system, do we need to change outwardly how we speak with that?
Oh.
No. So then we can imagine all the changes we're going to make now will happen internally. So the internal variables are varying variables. Okay, so we're going to change the varying variables, which have nothing to do with how we talk to the system, only how the system talks internally. We're going to change the code. And if we're going to change uniform variables, we're only going to move them from one shader to another shader. We might have to do that, but we're not going to add uniform variables or remove them. So then let's just start with this. Let's go through our variables and decide how we need to change those. So model matrix, view matrix, and projection matrix. Do these still belong in the fragment shader? No, in the vertex shader? Or do we want to move them? Still in vertex shader? Diffuse, specular, shininess. Where do these belong now? Or where will these belong now? Fragment shader? These are integral parts of the lighting calculations. And since we're going to move our main lighting calculations to the fragment shader, we would expect these colors to move. All right, so here we're putting the diffuse and the specular and the shininess into the fragment shader. How about light position, light color? We imagine are part of the lighting calculations. Again, we're going to take those, move those here. So we have light color and the material intensities and all that. How about light position and eye position?
No.
Yeah, we use those in the vertex shader to calculate the vectors. If we were to just send positions over and then calculate the vectors in the fragment shader, we could find ways to do that. But the simplest way is to say, we don't want any positions in the fragment shader. We don't want any absolute positions. We just want kind of relative directions. And if that means we actually send the vectors, which are true directions, that's fine, as long as we send these different directions that have a relative relationship to one another. So then the question is, we don't want to have a varying variable for color anymore, because we're going to actually calculate the color here. And the question is, or well, we went through this. We want there to be a varying variable for S. We want there to be a varying variable for the normal. We just call it Vn actually. And we want there to be a varying variable for the halfway vector. So this code doesn't change. Here I'm changing the position, here I'm changing the normal.
Shouldn't that be then equal to Vn?
Yeah. So we could just do V underscore n equals, and then we could actually take this instead of this and just throw this away. So okay, we have this here. We multiply it with a model matrix. This is going to be V underscore n because we don't really need to use the normal here in anything else. All right, so instead of vec s, making a new vector, we say this is just going to be V underscore s. We need to make this vector V here, or we could do it in one line, but let's simplify this a little bit. And then we say, well, V underscore h equals S plus V.
It has to be V underscore S.
Yes. V underscore S plus V, which is just the one we made here on the fly. All right. These calculations, however, are going to have to move. We take those into the fragment shader.
But you need to add your varying variable.
Yeah. So anytime we change varying variables, we can be pretty safe to just take our entire set of varying variables and paste them into from one shader to the other because they should match. So that's fine. Now we have matching varying variables. So now we have to take their names and say instead of normal here, we have this V underscore n, V underscore n here, V underscore s, V underscore h. Take their lengths.
You have a V underscore double H.
So Then I have Lambert and Phong, and I just made them here. So V color, do I need that? Not really. I don't have any V underscore color. So I just set fragment color directly to this. Obviously, this will be more complicated when you have more lights and all kinds of things. But with this simple light model, with one light that we have now, this may be enough to move these calculations over. First thing we'll do is try to run it just to see if okay, we didn't compile these shaders, did we?
Yeah, in the fragment shader on line 17 there is a
Is there a mistake? Let's see, the fragment shader, line 17, float Lambert.
You have double S.
I have a double S, okay. We can leave it in there though and see it actually. So let's make sure it's the pixel lighting version that we're compiling here. Okay. So this, it didn't crash, but it didn't work either. So V underscore SS, undeclared identifier, fine. So this is always nice to have, to actually be able to read what the errors are. Let's see now if we get. Okay, this looks a little bit different from what we had earlier, right? Looks super smooth. Go here. Don't see any of that stuff anymore. Better? Does it look more different than you expected? Is it more of a change than? There's something happening here though. You can see that by just going closer and further away. Well, some things here that are actually affecting the position of this. Or shouldn't. Still, by going closer and further away, we're also changing the angles. All in all, it looks pretty good. Here, I feel that it should, when I'm close. Something with the lengths has an effect here as well. We can try out things with a small system like this that may be a little bit expensive, but just to see if there might be effects. Something like, let's normalize V underscore H before we send it over here. And for S here. Sometimes, you know, there can be little floating point errors when one vector is very long, like the vector that we take our position minus something else.
Why are you normalizing?
Here I was going to normalize V, just to see if we can normalize all of them and see that makes a change. Whereas normalize, it's a
Normalize return something.
Yeah, it returns something. That's true.
Let's say V equals.
Yeah. So we'd have to do it like this. Normalize everything that we're sticking in here. It's expensive, but in some cases, you know, we can just look at the result and decide: is this better enough that it's worth doing something like this? Is it not? Because in the end, all of this is simulations. So now I'm normalizing this, I'm normalizing this, I'm normalizing V. So I'm keeping them equal length so that we don't have kind of one very short vector that might be the normal and one very long vector. And then we're doing the halfway vector between those. That might be a big thing in that, yeah, if we have because when we're close, then the vector pointing to us, to the camera, is very short. But the vector pointing to the light is longer. And then the halfway vector will be often more influenced by one than the other, and then we won't get the same kind of range there. Let's get this, change the effect. Yeah, now I can see even when I'm close, it's kind of moving towards where I am.
What happens if you go behind the ball? You shouldn't be able to see it at all.
Yeah, there's this little shine kind of on the edge if I go all the way behind.
There you go, it's gone now.
So maybe I went behind the box as well. There it is. I'm just going to see if I can go behind it, see if it appears on the other side. Okay, went into it or something. See, without any reference, it's kind of hard to always know where you are. So right behind it, no, nothing's there. Then I go to the other side and it kind of appears on the other edge. So now being closer or further away doesn't affect it as much as earlier. So if I normalize them, I keep them in the same kind of range of lengths, and this halfway vector isn't affected as much by these changes. However, in the end, this normalization can be costly. I am doing it in the vertex shader, however, which is very much better than doing it in the fragment shader. Then we could actually go ahead and say, well, if everything comes in here normalized, we are doing gradients between these normalized vectors, so they won't all be exactly unit length, but maybe they'll be close enough that we can say, let's save somewhere else. Let's normalize them all there, and then let's skip these lengths and just say, I need this. Make sure I take exactly correct amount here. Like so. And let's take here as well. Okay, this crashes. So syntax error. Parentheses. Yeah, I should have taken one more off here. This is very much different again. Okay, can you see what's happening here? Closer to the vertices, they're unit length. But when I do the gradient, you see how we can see how doing a gradient between something like this. If I have a normal that's here and it's unit length, and I have another one that's here and it's unit length, the weighted average in the middle, for instance, is not going to be along this arch. It's going to be along this line because I'm just taking a straight average. I'm just taking an average of the values, which means it'll be shorter than unit length. So the lighting calculations will be a little bit affected over the range, but they'll be actually completely unit length here. So the effect, you can see that it's going to be brighter along the edges, particularly, and so we're getting our old problem back here. Looks kind of cool though. So maybe in some cases this is an effect we like, some cases not. That's in that case. And so we just go back to what we had. Okay, this is our best system, our most exact system. And length, identifier. However, it's a little bit costly because we're doing those normalizations in the vertex shader. But at least we're not doing these full normalizations in the fragment shader. So then you can skip the normalizations as well and just look at the system. Is it good enough for my game or for my program or for my simulation? If it is, it's good enough. So, okay, what we've done now is basically taken our entire set of calculations or lighting calculations and moved them from the vertex shader to the pixel shader. So now we have fragment lighting rather than vertex lighting. Have you heard these ideas thrown around? These reference to this pixel shading or vertex shading or fragment shading. This is basically what it's talking about. Like, how much of your calculations do you move to the fragment shader so that you can do them for every single pixel? This will give you more exact calculations, but it'll give you a lot more costly calculations. Because now we have to do all these lighting calculations once for every pixel rather than once for every vertex. Another thing, since we split this up, and we have a little time before we take the break, so let's do that now, is we can work with more than one shader at a time. We can send some objects through one shader and other objects through another shader. So I'd actually like to do that now and kind of look at what we need to do in order to keep track of everything and what values we have to resend when we switch between shaders, stuff like that. So let's start by making a new class. Let's call it shader. So what we want to do here is we want to abstract a little bit away from this class here, this code, all this shader code. So we want to take all of this and put it into some shader class and say, I have a shader class and it oops. And it kind of keeps track of everything that I need to do to talk to the shader, sets the color and so on and so forth. So to begin with, let's see. Shader. I have a constructor here. When we build this, we would like to do all of this stuff, more or less all of the shader stuff that we do in here, we're going to do in there instead. Rendering program ID, and then we're going to stop. Yeah, all of this has to do with other stuff than just the shader. Then we need to find all of these variables that we need, that we had here, like rendering program ID, fragment shader ID, here. Okay. So we kind of need to send this in as well. Well, we can actually just do this over here and say the game itself will start by setting the input processor, and the shader should work from then on. All right, then we need all these location variables. So those are now I'll have to do with the shader. Like so. Shader has all of these. So now the shader should work. But now we have errors all over the place here where we're trying to send in these locations. Okay, there are more changes that we need to do, because now we're sending these location identifiers from the shaders directly into BoxGraphic. But if we want to sometimes draw a box with one shader and sometimes with another, we have to make sure that we're sending this in a different way. So we can't create the box with that. So instead, we're going to have to say, all right, we can't take the normal pointer in here. We're going to have to take the normal pointer in when we draw it. We can't really store the normal pointer, instead it's, yeah, and the same with the vertex pointer. Oh yeah, of course. Just take the entire thing, like so. So both of these, oops. I'm going to start by doing this. In the end, we'll probably want to send the shader down there or something like that in order to, so clean this out and say what we need to do in the end is we need to send the shader, the current shader that we're using, into these functions so that it can just ask that shader for its normal pointer and vertex pointer and so on and so forth. We're going to make sure in the shader that these are public. Simplify this for now. You can then go through it and decide what actually needs to be public and what needs to be private. All right. Save everything and just say here, let's send the shader into this. Shader. And you can go in here and say shader dot, and vertex pointer is probably one of our possibilities here. Or in this case, actually, position, location. You can make this cleaner as well. Dot normal location. By making functions on the shader, like get normal position, get vertex, or get vertex pointer, get normal pointer. Spawn. Here. So what we then do is to say just let's have a shader here. Private shader. And create. We'll go ahead and do shader equals new shader. And all of these places will send shader in there. And we can just skip creating these and not use them for now. However, we're going to use sphere graphic and we're going to use box graphic. So no, actually, I'm not going to do it this way. Let's not send shader in here. Let's instead send shader the other way we did here. Do the same for sphere graphic. So to go through this again, I'm skipping the vertex pointer and normal pointer. Skipping these entirely. Instead, we send the shader in here. And we use shader.position location. Vertex pointer. And shader.normal location. For the normal pointer. And we need to do shader here as well. A little bit of refactoring here. Here, we still have errors because all the places we're calling this. So model matrix main, set shader matrix. How does this function work? Okay, so we are going to stop storing a shader matrix pointer here. See what errors we get. Why is there an error here? Skip this, we can throw this one out and instead say we're going to send in here shader. Okay, we're going to do it like this. Send this directly in. Sometimes it's the view matrix, sometimes it's the model matrix. So here we're going to do shader dot model matrix location. Some more spots here that we're doing this. Okay, and now we have a bunch of these places where we can see GL uniform matrix. We're sending the view matrix location, for instance. What we can do two things here. I can either just go ahead and say, okay, I'm just going to use shader dot view matrix location, or I could go ahead and make functions in the shader, which would probably be nicer in the end. To say the shader just has these functions, which are called set view matrix, set model matrix, change color, set material, diffuse, so on and so forth. Then I can also make this code a lot cleaner. So if you want to take a break now, you can do that for like 5 minutes. I'm gonna refactor this code a little bit and go through the changes. But if you wanna sit through that and watch, then that's fine, either way. But in about 5 minutes, I hope I'll have this kind of set up and refactored so we can continue on with our idea. I at least have this running. What I'd like to do as well is to kind of simplify the code as well and move more of this into the shader. So what I'm doing now is I'm just simplifying camera code a little bit. I'm taking it out of the game class as well. So the camera itself also does the projections. So we definitely don't need any of this. I'm not doing any orthographic projection here. I'm basically skipping this. I have cam look here. Except we should take this low, so actually make the camera first. Okay. So change that. Let's first see how we can go without it starting to clip. Okay, this is fine. 40. Okay. Hop on the y-axis. Adding some motion in here. Back up over this. Okay, both are going up. Forgot to add the minus here. Right. So I've got the code working again. We have all these lines here. We're doing something like setting a uniform variable with this code, and then simply calling shader.lightPositionLocation. Where for something like this, for instance, it'd be nicer to go into the shader and say I'm going to add a function here. Say this is void function, public, and it's called set light color. Red, green, blue, and alpha. And inside that, I do something like this and say I'm going to take light color location. Set this here, then I don't need to obviously reference the shader specifically. But this, then I'm going to take light color location, make that private. Just in order to see where there's an error. Okay, so no error. But we instead have to say shader dot set light color. One. In order to get some color on the light. Okay, so now I'm kind of moving this shader specific code into the shader class. Diffuse, specular, light position, we can move all of these things. Go ahead and make exactly the same kind of thing for material hues. The one for material specular. And we're going to use material hues location, specular location. Add one for shininess. Material shininess. Except that one only takes one variable. One F. And we send in shininess there. And we take shininess location. All right, so then we can take all of these and make them private as well. And then we can see where are these changing, or where do we need those. So instead of doing shader dot this, we just do shader set material diffuse with these same values. Shader dot set material specular, these values. Shader dot set material shininess value. Okay. Again, we're just cancel. I guess we need this again. Color in this case. And we had full shininess. Right, so again, things are working. We're just kind of moving things around. The wrong color in somewhere here, or is it possible that in shader, in the function we copy paste something? Diffuse, do shininess. Can you see if I'm doing something in particular?
Value
Yes, it's true. So here we should always be doing red, green, blue, and alpha, obviously. We can move those over here. So, all right. Now what I kind of wanted to do was to say, let's go into this function here, and let's make another sphere. So this one was not translated to anywhere. So let's translate one of them to -4, and the other one to 4. So the translation should be after the push. Okay, here as well. Change the image a little bit. A little bit closer. So I'm drawing the cube here, -10, -4, and the other one is also -4. So if we stick 4, we have push, we have pop. Okay. And I'm doing it in the wrong dimension, aren't I? Or actually doing the other stuff in the wrong dimension. This should be minus 10, just 10 in Z. Then we should put the camera there as well. So where we do cam look, should also do it in Z. And then this one should be minus 10. All right, so now we have two tweeters here. And we're going to change the light position as well. Light position to 10 in this direction. Now I have two spheres here. The idea is kind of to see if we can draw each of these spheres with a different shader. So what I want to do here is to see if we can send some kind of variable into the shader and tell it to basically tell it which set of files it's going to use, which set of files it's going to compile. And since all of this code is more or less the same for both of them, since both of these systems that we have, the pixel lighting and the vertex lighting, since both of them use the same kind of outward set of variables, and we should be able to either just send in a Boolean here, just say, we build a shader here and we say, is it fragment lighting, true or false? We can simply go in here and say if fragment lighting one thing, otherwise we do another, and be vertex lighting. So to begin with, I can now say either true for everything, or I can say false. And switch to the other shader. But at least I can do this. I can decide which one I use for the entire system. In order to kind of build them both, we're going to need two shaders. Let's to begin with go ahead and say I'm going to have a shader called vertex shader or vertex lighting shader, another one called fragment lighting shader. And I would actually like, because in Java these variables are references, to have one that's just called shader still. So then we can do something like with skip, or, right? Copy this and say vertex lighting shader is a new shader false, fragment lighting shader is a new shader true. And I'm going to say shader equals one of them. Vertex lighting shader. So that's the one we're going to be using when we're doing everything from then on. However, we need to make sure that we switch to it. So I'm going to go into the shader and make a function here. Public void switch to shader. that case, we would simply call this function here. So I call GLU's program with my rendering program ID, which this particular shader got when it built this particular rendering program. So I should be able to switch to either one. So now I've compiled both, and I switched to one of them. Okay, what happened now? I didn't call switch to shader. So what happened here is it builds the vertex shader, then it builds the fragment shader, then it sets the vertex shader to shader. However, the last one that was built was this one. If we were to do it the other way around, set it to fragment lighting, that would work. Right. However, I want to set it to vertex shader. So, except then I have to make sure I switch to it. So I can say shader dot shader. And then we're using this one. Now what I want to do is I want to go ahead to here and say, all right, I'm using the vertex shader now, but I'm just going to jump in here and say, I want to use the fragment lighting shader and switch to that for this sphere, and then I want to switch back for the other sphere. Do we expect this to work completely? Okay, so one of them is displayed. One of them disappears. Why is that? So the reason here is that while I didn't have that switched on, I was setting a bunch of variables. I was setting a bunch of variables that I then only set into the vertex shader or into the vertex lighting shader and not into the fragment lighting shader. So I need to make sure that when I'm, for instance, sending the camera position and all that, if I have two shaders and I want to be able to switch between them, I'm also going to have to send all of this into both of them. I have to double all of this light position location. Double this, and I'm going to have to call it for both of them. Let's just steal these lines for a moment here. Does this make sense? That if I'm going to use them both, if they're both supposed to be kind of representing the same system, I'm going to have to make sure that all these variables are set in both of them. Okay, so now I have these things set for both of them. Okay, not enough. But more things are not being set in both of them. For instance, up here, projection matrix. I have to make sure we do that for both of them as well. Things. Okay, we didn't set the model matrix either, except for one of them. However, we're going to have to do that down here. So if, for instance, in this case, we set the shader matrix. Okay, we set the model matrix actually. In both cases, let's see for now. So what more are we setting here? Here we set the shader matrix, the model matrix for this particular one. Since we switched the shader over to this.
Why not have a function in shader that sets the model matrix?
So it'd probably be a good idea to actually, when we switch to shader, that we also take all of the information that has been sent to the shader and kind of, or somehow that has been set in the shader beforehand, and kind of make sure that it's definitely inside the variables. So that would be, is that what you're talking about? Like,
yeah, or have a, like, if like you're doing, have your set, like your matrix dot model matrix dot main dot set whatever.
We'd like to inside here.
Yeah.
So we would like to do something like public void set model matrix here, and then we probably just want to take a matrix in here. This is the idea?
Yeah, and then you have it do both, or you can even have another variable that's like a 0, 1, 2. If it's 0, it sets it to both of them. If it's 1, it sets it to the fragment shader. If it's 2, it sends it to the just so it's cleaner and you don't have to, you're not forgetting about things.
Yeah, in this case though, we have kind of 2 instances of shader, each one that we have to send this stuff into. We could also have 1 instance of shader and just say, I'm going to make this shader class compile both, and then I just send it a boolean for, you know, what it's supposed to set. So yeah, this needs cleaning up. The main thing is though, so yeah, in this case, we then, instead of doing all of this, instead go ahead and say just shader dot set model matrix. Well, it would actually be view and projection matrix that we'd like to do. I'm going to skip that for a while. I'm going to get this working first. So yes, making functions that actually take in these variables rather than, so that we can do all this GL uniform stuff inside the shader class. Will make the code look a lot cleaner. However, what I am thinking right now is whether we actually need to take these things, so the fragment shader. One, I'm wondering if there's, okay, shader.set light color. Okay, that's one that we don't have anything for. So in that case, we should actually, when we set the light color, say we need to set the light color for this shader. We also need to set the light color for this shader. See if that's enough to get them both running. No. Shader fragment, vertex fragment, vertex fragment. Material diffuse, material specular, material Shannon. As we do that again though, after we switch to it, there is a possibility that we need to take all of these things. If we switch to it, then we need to set all of them again. Vertex fragment, vertex fragment, vertex fragment. Perspective projection. Let's see how that, if it actually needs to, be switched to it when we're setting these things. So okay, bear with me here. We're going to make the camera and we're going to do all of this. Here. Create this. And main. Okay, none of this really matters. Like so. Okay, then we're going to switch to the vertex lighting shader. All right, yeah, this is another thing, sorry. When we set variables, of course, those variables only work on the shader that we've actually switched to. So we're going to switch to the vertex lighting shader, and we are going to these things here. Clear color can be set somewhere here above. And enable depth test can be set above here. So we're going to do these things. All right, in that case, since we're making the shader anyway, we can do it like this. Switch to the shader, and we repeat this for the fragment lighting shader. We go down to here, rather than doing it we had it earlier. Again, bear with me here. We are going to go ahead here and we're going to do fragment lighting shader dot switch to shader. Let's start with vertex. These things here down below. And then I'm going to switch to the so okay, so the first one was vertex, the second one is fragment. Okay, so now I'm doing this while I have the shader switched on. Then we'll switch to the vertex lighting shader and also basically do it like this. So we don't always have to say vertex lighting shader, we can just say shader, saying I set this shader variable to the vertex lighting shader and I switched it on. Then I switch the fragment lighting shader on here, switch the vertex lighting shader back on. And we're hoping that, yeah. So now I have two different objects in the same scene, using the same lights and the same camera and everything, except they're each being drawn using a different shader. They, however, share everything else. They share an OpenGL pipeline. They share a depth buffer. So we can see that if I make one of them go behind the other, no, the one that's closer to me goes in front. If I go to the other side, something happens, one closer to me. So they share the entire OpenGL pipeline. The only thing that they're doing separately is the shader program. In one case, this smooth and nice fragment lighting, pixel lighting, and the other case doing a more coarse for vertex lighting calculations.
And you would do the for vertex if you had a non-smooth shape, so like a cube or a rectangle of some sort, where, yeah, or something with flat sides, where you do the per pixel lighting for smooth things most of the time.
Actually, we can look at the difference on the cube as well. So if we go ahead and say, let's draw the cube, which I think we drew here first, and say, let's do that with the fragment one. And let's actually add some specular to it so we see the difference more clearly. Closer here. See this, even on a flat surface, you can see how this kicks in here. And if we were to do it with the vertex lighting, go closer, and all I get is not much to begin with. You can see that it kind of goes over the entire thing. It's more of this gradient. So if we make two cubes as well, say let's just copy this entire code and do one of them with the fragment shader and one of them with the vertex shader. And take one of them, where do we translate them? -10, let's take one of them a bit up, 4 up, and the other one down. See if there's a big difference here when we go close to this one and go close to this one. See, this is kind of, actually see the light reflecting here more, whereas here you kind of see that it happens in a corner and then just gradient over the entire thing. Even if I go closer, I'm not getting any more exact result, any better result as such. Go up here though, go closer. No, you can see it's actually happening for each pixel. It's not a gradient just going over the entire thing. Does that answer the question? So in general, if we have per pixel lighting, we'll be doing that on kind of the entire scene. Then if you have objects that are flat, have flat surfaces, and really don't have much shininess or much interesting lighting going on anyway, just have kind of matte surfaces, then yes, you could get away with just using vertex shaders or per vertex lighting, and in that way kind of make your calculations a little bit cheaper. Okay, so this took a while just to get this kind of going, and it would take more if I wanted to refactor it properly. I'd say for every single place where we're inside our code here, doing something like GL uniform something something, sending something into the shader, we should instead go ahead and go into the shader and say, I'm going to make a function for this. So if we go into the shader and make a public void set view matrix set view matrix, and set view matrix has a float buffer, so we do that. Takes in a float buffer. Let's call it mat. Go ahead and take this code here and say, stick that in here. Instead of cam view matrix, we just send this buffer that was sent in. And here we simply use view matrix location. Okay, so now we simplified this a little bit. And the code where we call it is we're going to take view matrix location now and make it private. So we can't just access it directly. Instead, we have to go in here and, okay, now simply go and say shader dot set view matrix and dot get view matrix, and the same down here. And of course, it would be nicer to actually do it like this. So this out, this in here, put it here. And we don't actually need to explicitly state this. And then we could also do it in a loop. When we actually want to make this even cleaner, we can go ahead and say, all right, instead of doing this, I know I'm going to have to do these things twice, or once for each of these two shaders. We'll just do a for loop. For I is 0, I is less than 2, I plus. Then I simply say, if I is 0, I'm going to switch to the vertex lighting shader. Else, I'm going to switch to, or set the shader to fragment lighting shader. And then we can simply do this once. That is, we switch to the shader that we set shader to, and we use shader here, and then we can take this out. So now I've simplified this as well. I said, okay, I'm going to do all of these things exactly the same to both of the shaders. I can simply do it in 2 loops here. If I have more shaders, I can just skip, or I can just change which shader is being set. And then these main variables here, like the camera position and these things that are just set once, I can set them in this way. And then anytime I want to switch between them, I set the shader to this, switch to it, and then the code is exactly the same. And as we continue, we take more and more of these things and stick them into the shader itself. One thing that we haven't done, we haven't taken the entire set of possible values that we can do in lighting calculations. So we've done the diffuse and we've done the specular lighting. Those are kind of the ones that matter the most. But if I was to take my shaders here and add to them ambient lighting, for instance, say, okay, I want each light to have something that light adds to the ambience. And then the materials are, affected differently by the ambience. Yeah, so we have light position. That would happen in the pixel shader here. So for the pixel lighting or per fragment lighting, this is something that would happen here. Go ahead and add uniform spec4 u_material ambient. I'd actually like to add light ambient as well, so we don't have like a fully white light and that's what happens to everything. In some cases, we'd actually say we'll have spec4 either a global ambient, which is just the entire ambient, or we'll have one for each light. In this case, we only have one light, so I'm going to say light ambient. However, I might say the ambient is kind of how much the light fills the room. But the material should really be affected by this extra light, just in the same, it has the same color as the diffuse, right? I could also say that I'm going to add the ambient to the light. I'm going to skip the ambient on the material and just use the diffuse. How would this add to the, we don't need to calculate a new Lambert or a new Phong. What we then do with the ambient, it just adds to every single side. So then we take u_light ambient times u_material diffuse. So we have the ambient added. However, then we have a new variable here. That variable needs to go into the other shaders as well. So we have another set of shaders, which are the vertex lighting. Then we'd go into the vertex shader there, because we're doing the lighting calculations. Vertex shader there. We go into here. U_material diffuse. Light position, light ambient, light color. We can steal the extra line of calculation that we added here. Something like this. So we're adding that here. This means that in my shader, I need to add a new variable, which is light ambient. Light ambient location, I need to add a new light ambient. Add a new handle. I need to add a new function to set it. Ambient. Right. Having the shader class, however, makes it a little bit more simple to add these things. And then finally, I'd like to set it where I want it to be. So let's just set it to one of these objects to begin with. Let's just set. dot. Well, this is the part of the light. Let's just see how it looks if we just add it to the entire scene. Do it in here. Light color, light ambient. Let's say this should be some low. Remember, not too low though, so we can see it for the first time. Files or if it crashes. Okay, everything got a little bit brighter. The main thing though is when we kind of walk behind it, these things don't completely entirely disappear. Instead, we kind of have a little bit of mass all the way around. Okay, something going on there in our lighting calculations. It makes the vector actually, for whatever reason, go around. Okay, so they have a little bit more mass this way. Let's lower it here. Let's make the light ambient 0.2. But it can make a difference to have a little bit of this ambient light filling everything, just in order to kind of see the objects, so they don't entirely disappear. This is nice. You can see where they are, but it's not. It feels a little bit more like it's inside a room. Something off about the specular calculation here, but that should be fairly easily fixable. This one is nicer anyway, so stick to that one. Now we have ambient. Another thing we can add is we can add material emission. Basically, the light that the object gives off itself. Like the object actually is a light source itself. That doesn't mean it lights other things. It just means that it shines. So if we add this,
We're missing a vec or
yes, vec4, put this in here and in here. Material emission. Ennþá einhverja mínútur eftir. All right. Emission. How would we add that to our calculation? Simply U underscore material emission. It's not. Ég á alveg 2 mínútur eftir að tímanum áður en að 3 mínúturnar byrja. Þessi klukka?
Þessi korriður.
Mín klukka heyrðu. Já, þá tíminn búinn. All right, I'll add to this later. So, okay, the idea with emission, what I'd like to do, and I might add a video on that, is actually use emission to kind of represent the light source itself. Make a little sphere where the light source is, so we can actually see the light source itself, because now the light is just kind of an idea rather than an actual object. Stop lähetada. Stop.